before we continue to the next to the examples, and maybe it will be nice if we can repeat again, review again a little bit about what node analysis, not loop analysis is about. So basically, it is one of the method to conduct circuit analysis, but using Kirchhoff voltage law instead of Kirchhoff current law. So in Kirchhoff current law, we are interested in knowing the node voltage, the node voltages. So to know the node voltages, we use Kirchhoff current law to first determine the currents and then calculate the node voltages accordingly. Loop analysis, on the other hand, we are interested to know the current flowing through the branches, current flowing through the branches. So in order to find that, we first determine the voltage across. We write the Kirchhoff voltage law in terms of the voltages across the components in the branches. So from there, we can find the loop currents, and from the loop currents, then we can determine the individual current at each branch using the Ohm's law. So this is the second systematic technique to determine all currents and voltages in circuit, only with different order compared to node analysis, complementary to node analysis. So when do we use node analysis? When do we use loop analysis? That will be subject of in the last part of this chapter, about how to. That depends on the circuits. So we have discussed how to write the Kirchhoff voltage law based on the by writing first. So this is Kirchhoff current law. This is not analysis. This is the reviewing the previous section. So if the case is like this, if there is only a single loop, so there is only a single current flowing through, it will be easier to write one equation to find that current, and then afterwards calculate the node voltages. So that is the use of Kirchhoff voltage law, or in loop analysis. If we had used node analysis instead, then we would need these three equations to compute all the node voltages, using Kirchhoff current law. So after applying Kirchhoff voltage law, then we can use Ohm's law to express the voltage in terms of the loop current. And then we can find this I, one equation for one loop current. So afterwards, then we can calculate using Ohm's law individual voltage across each of the components. Okay. So yesterday we have also defined what loops are and what meshes are, and also what loop currents are. Okay. So a loop is basically a closed path that does not go twice over any node. If the loop doesn't enclose any other loop, then it is called as a mesh. Okay. A mesh is a loop that does not enclose any other loop. So in this case, F, A, B, E, F, and E, B, C, D, E are meshes. Then we define a loop current, which is a fictitious current assumed to flow around a loop. So in this case, then I1, I2, and I3 are loop currents. This one, I1, I2, and the outer loop currents. A mesh current is a loop current associated to a mesh. So in this case of circuit, then the mesh current are only the I1 and I2, and I3 is not included. Okay, so we have discussed this yesterday about how to derive the loop currents equation. And then we have also examined yesterday the theory to determine how many loop equations we will need if we know the number of branches and the number of nodes in that particular circuit, okay, which has this formula L equals to B minus N minus 1. So we have yesterday tried several example, and then writing also the Kirchhoff voltage law on the left mesh and on the right mesh. Then replacing it and rearranging it based on the current terms, the loop current terms. So this is the difference. If in the node analysis we arrange the equation in terms of the node voltage terms, yeah, V1, V2, V3, etc. Well, this one in terms of the loop currents. Then we can express that in matrix form. So if we have a computer, we can solve it using MATLAB, or even in some calculator, now they have this facility to calculate the solution of matrix. Okay, so we have discussed this and we have learned a little bit how to write mesh equations, identifying all the voltage drop and writing the Kirchhoff voltage law on each of the mesh. Here at top mesh and then bottom mesh, then using Ohm's law to replace that voltage with the loop currents and the corresponding resistor. Then rearranging according to the current, to the loop current, and finally we can find the loop currents, and then we can calculate the branch currents, or otherwise also calculate the voltage across any components in the circuit. So usually by convention we use clockwise, yeah, to orientate the loop current, but in actually it doesn't have to be clockwise. You can also draw counterclockwise, but normally we do it clockwise. People do it clockwise. After we determine the loop current, then we write KVL, Kirchhoff voltage law, for each of the mesh, and applying Ohm's law to every resistor. So then the voltage term becomes current multiplied to the resistor. So what we need to be careful is each of the loop should follow the passive sign convention, yeah, using the loop current reference as the loop current reference direction. So then from that you determine whether the sign is positive or negative. So whenever an element has more than one loop current flowing through it, we compute the net current in the direction travel. So in this particular example, the R2 has two loop currents flowing through it, yeah, the I1 and I2. So here then we compute here I1 minus I2 in the direction of the travel of the loop current. Okay, now we start to learn several examples from how to solve several circuit examples using Kirchhoff voltage law and loop analysis. For example, we have here two independent voltage source, 12 volt and 3 volt, and it has two mesh. Yeah, basically, it can also have three loops instead, but two mesh will be enough. So we have 6 kilo ohm here, 3 kilo ohm, 6 kilo ohm, and the question asks us to determine or to calculate I0 or I output, yeah, that the current that flows through the 6 kilo ohm branch in the middle. So first is you do not need to really assign polarities in the resistor. We can just apply Ohm's law to each element when we write the Kirchhoff voltage law. So for example, in the loop current 1, I1. So from here, it is increasing. So remember, usually we assign using passive sign convention, and passive convention is based on voltage drop, right? Because the current flows through the positive terminal and going out from the negative terminal. So passive sign convention is based on voltage drop. So for example, when in this first loop, I1, current enters to the independent 12 voltage source from or into its negative terminal, then we know that we have to put negative sign. So because it is opposite to the passive sign convention. Or in different words, basically this 12 volt is when the current flows from the negative, the potential is being increased. So it is a negative voltage drop. A positive voltage increase means equivalently to negative voltage drop. Yeah. So negative 12 plus here 6 kilo ohm I1, then here 6 kilo ohm, the next 6 kilo ohm, there are two loop currents flowing through it. The first is I1, the second one is I2. And since now in KVL, in this loop current for I1, we go according to the direction of the I1 loop current. So I1 will be positive, while I2 will be negative. So here plus 6K multiplied to I1 minus I2 equals to 0. At the loop current 2, then if we depart from this part, yeah, from this reference here clockwise, so according to the direction of I2 loop current, then it will be 6 kilo ohm multiplied to I2 minus I1, because there is I1 here flowing through 6 kilo ohm resistor here in the middle. Then here only I2 loop current flows through this 3 kilo ohm, so we multiply the 3 kilo ohm resistor there with I2, and then it enters the independent voltage source, the 3-volt independent voltage source from into its positive terminal, so it follows the passive sign convention. That is why the sign is positive. Positive 3 equals 0. So after this, what we need to do is rearranging the terms such that the loop this group according to the loop currents. Okay, so rearranging, then it becomes 6K I1 plus 6K I1 becomes 12K I1 minus 6K I2, then the constants, which does not have any variable multiplied into it, move to the other side of the equation, so equals to 12. KVL I2, that becomes negative 6K I1 here, then 6K I2 plus 3K I2 becomes plus 9K I2 equals to 3, move to the right hand side of the equation, becomes negative 3. So from here we have two equations with two unknowns, I1 and I2. Here, for example, we can use substitution method. We multiply the second equation with 2, so this becomes negative 12K I1 plus 18K I2 equals to negative 6, right? So when we then add them, so the I1 terms will be eliminated. So this becomes minus 6K I2 plus 18K I2. Okay, so becomes 12K I2. Then 12 multiplied to minus 6. 12 plus minus 6 equals to 6. So 12 kilo I2 equals to 6. I2 equals to 6 divided by 12 kilo, or half milliampere. Okay, so from here then we can calculate further the I1 as well. So 12K I1 equals to here equals to 12 plus 6K I2. And then we substitute the I2 with 0.5 milliampere here, and then we obtain I1 equals to 5/4 milliampere. Okay, express the variable of interest as function of the loop currents. So here, the variable of interest that is asked by the question is I0, I output, and depends. So if we know here, the I0, the direction of I0 here in this branch is drawn with the arrow pointing downward, right? So this pointing downwards is the same as the direction of loop current I1. So then I0 equals to I1 positive here, positive I1, and negative I2 here. Okay, so 5/4 milliampere, negative 0.5 milliampere, or how much is that? So this becomes 3 over 4, 2 over 4, so becomes 3 over 4 milliampere. Alternatively, we can also choose not instead of mesh currents like in this one, because this I loop current I1 does not enclose I2, and similarly vice versa. I2 does not enclose I1 either. We can have we could have chosen instead the second loop is the outer loop. Okay, so here I1 is the same as this first alternative here, from this node going to this node back to that node. But we can choose the second node, not this mesh, but instead from the same node here, the reference node, going through this minus 12 volt, going to the upper part of the resistor, again going to the next independent voltage source, yeah, the 3 volt here, and then going back to the original point. Okay, so from here then KVL at I1 will be minus 12, similar to the first way to solve the problem, minus 12 plus 6K. I1 now, however, the difference now here is that here, yeah, on the upper part here, there are two loop currents flowing through the upper 6K here, I1 and I2. So we have to write it minus 12 plus 6K multiplied to I1 plus I2 here. Then the second 6 kilo ohm, only I1 flows through it. So then we just write plus 6 kilo I1 equals to 0. On the second loop, on the other hand, first here, from here as well, minus 12. Sorry, the letters writing is upside down. So minus 12 plus 6 kilo, and on this resistor, there are two loop currents flowing through it. So I1 and I2, this I1 and this I2. So plus 6K multiplied with I1 plus I2. In this one, 3K only I2 flows through it. So plus 3K I2, then there is voltage drop here, plus 3 volt equals to 0. Since in this case, the current, the IO, yeah, is the current flowing through this branch, the 6 kilo ohm branch at the middle. And the loop current that flows through that branch is only I1. So in this case, then if we use this method instead of the first method, then I output will be equal to I1. Yeah, or in this case, we will obtain also this part, yeah, from the formula. So this selection is more efficient, yeah, because this variable of interest IO is the same as one of the loop currents. So here, from by rearranging again similar way like the previous example, then we obtain I1 5 over 4. We find instead 3 over 4, 3 over 4 milliampere. Why is it not the same? Yeah. It should be the same. If the circuit contains only independent source, like this, like the previous example as well, the mesh equation can be written by inspection. Okay, so must have all mesh currents with the same orientation. So in this case, the orientation is similar clockwise. Okay. Then in loop K, the coefficient of IK is the sum of the resistances around that loop. So the right hand side is the algebraic sum of voltage sources around the loop, which is equal to voltage rises negative voltage drop. Okay, so you put the voltage, the value of the independent voltage source on the right hand side equation. The coefficient of Ij is the sum of the resistances common to both K and J and with a negative sign. So for example, here in loop 1, so it will be this voltage source, okay, will be no need to put, yeah, you can immediately put on the right hand side of the equation equals to 12. Then here 12k I1 minus 6k I2, because this comes from the 6k I1 plus 6k I1 here. Yeah. So the coefficient of Ij is the sum of resistances common to both k and j, and with a negative sum. So here, this one, the I2 will have a negative sign because it goes opposite to the loop, the first loop. So in loop 2, so this becomes, if you put it on the right hand side, it becomes minus 3, okay, because there is a voltage drop here in the left side, but if you put to the right hand side, it becomes voltage increase, and so becomes minus 3. Then the component due to I1 is this 6 kilo ohm. Okay, so that will be I2 minus I1, right? Multiplied to 6 kilo ohm in this direction, plus I2 times 3 kilo ohm. So the I2 component will be 6 plus 3, 9 kilo ohm. The I1 component will be negative, because we are now investigating this mesh, not this mesh. Okay, so be careful that the sign may change. So as a practice example, let's say here we have 3 meshes, right? 4 kilo ohm, 6 kilo ohm resistors, and then 9 kilo ohm, 3 kilo ohm, and 12 kilo ohm. The voltage, dependent voltage source is 6 volt. Yeah. Actually, for me personally, it will be just easier to write it down a little bit more, then regrouping it rather than this way. So this way is immediately you put which the value of the resistor, and then multiplied with the I1, the loop currents. But sometimes you don't, you want to be more thorough, so that we can check the answer, and we can go according to the previous slide example. So go from one by one. So for example, in loop 1 here, the upper loop, or we can also call it as a mesh because it does not enclose the other loop. So the coefficient of I1 will be 4 plus 6, right? Because here 4 plus 6, 4k plus 6k. Coefficient of I3 in this loop will be negative, right? Negative 6k. Coefficient of I2, we don't know because there's no resistance in the independent voltage source here. So in this case, we just put 0. Yeah, because then this independent voltage source will be moved to the right hand side of the equation. Then coefficient of I3 will be this 6 kilo ohm, but having a negative sign. Okay, so as stated in the theory here, the coefficient of Ij is the sum of the resistances common to both K and J, and with a negative sign. Okay. Coefficient of I3 in this here will be negative 6K. So then from here, the right hand side of the equation is negative 6 volt, right? Because here there is a voltage drop, 6 volt. So when you put it on the left hand side, it's positive, but when you move it to the right hand side equation, it will be negative. Okay. So be careful with that. So if we write it completely, 4 plus 6, 4k plus 6k multiplied by I1, negative 0, I2, then negative 6k here plus multiplied to I3 equals to negative 6. Negative 6 is this one. Yeah. Then in loop 2, the I2 component is 9 plus 3. Coefficient of I1 is 0 because it only flows through this independent voltage source. Coefficient of I2 is 9 plus 9k plus 3k. Coefficient of I3 is negative 3k. Yeah, because this loop goes against the loop in I2. So the right hand side equation will be this one, negative this if according to the direction of the loop current, this is a voltage increase, yeah, the voltage increase. So it becomes negative in the left hand side, it becomes negative 6 volt. But then you move it to the right hand side equation, so it becomes positive 6 volt. Okay, so from here, then we write it down: minus 0 I1 plus 9k plus 3k I2 minus 3k I3 equals to 6. So we have already two equations, this one and this one. You can have the third equation by examining the loop 3. So current flow, the I1 coefficient will be coming from this one. So since it goes against the direction of the loop I3, so we assign negative sign to that value of the resistance, 6k. The I2 component will be contributed by this 3 kilo ohm. So also it goes against the loop I3, so we have to assign negative 3k I2. What about I3? I3 is here. So the coefficient will be 3k plus 6k plus 12k. Okay. Let's do another example. Using mesh equation to find the V output. So here the V output is the voltage across this 6 kilo ohm resistor. Okay, there are two independent voltage source, 6 volt and 3 volt. First is to draw the mesh current. So here we have two mesh, right? The first mesh here on the left and the second mesh here on the right. So the first mesh I1 with mesh current I1 flowing from this node and then through this 3 kilo volt voltage source, then go back to the original node. Current I2 here, yeah, and so then we write the mesh equation for KVL at I1. Yeah. So the I1 component will be 2K plus 4K plus 2K here, multiplied to I1. Component from the coefficient of I2 will be here negative 2K I2, yeah, because it goes against the I1 loop current. Equals what? Since here there is a voltage drop, so plus 3 volt in the left hand side. When you move it to the right hand side, it becomes negative 3 volt. Okay, understood, yeah? Then second mesh is on the right side here. If we depart from the coefficient for I1 will be this part, yeah, 2 contributed from 2K. But since I1 goes against the direction of I2, so we have to put negative 2K sign there. Okay. Then the coefficient of I2 will be 2K plus 6K, yeah, multiplied to I2. What about the voltage source? The voltage source here, it is voltage increase, so negative 3. This is also voltage increase, negative 6, negative 9 at the left hand side. So when we move to the right hand side, it becomes positive 6 volt plus positive 3 volt. Okay. After that, we can solve this equation because all the terms are already grouped according to the loop currents. You can immediately put this as coefficient to the matrix. Okay. Then solve it using Octave or MATLAB. Yeah. Otherwise, if it is still easy enough, yeah, two variables with two equations, then you can use elimination method or substitution method. Yeah, if you divide by 1k each of the term, then you get more small number. So this becomes 2 plus 4 plus 2 minus 2 equals to minus 3 divided by 1k. For example, something like it becomes milliampere. So this is the case. 8 for mesh 1, it becomes 8 minus I1 negative 2 I2 equals to negative 3 milliampere. Mesh 2 becomes negative 2 I1 plus 8 I2 equals to 9 milliampere. Okay. Then we do elimination. method, we multiplied this second equation with 4. Okay, so that then the I1 can be cancelled or can be eliminated, and we obtain minus 2I2 plus 32I2. So it becomes 30I2 equals to minus 3 multiplied to 36 equals to 33. Then you obtain I2, and because what we are concerned is V output here. V output here basically equals to I2 multiplied to the 6 kilo ohm, right? According to Ohm's law. So here we obtain V output equals to 6K multiplied by I2, which is 30, uh, 33, yeah? 33 milliamp. 33 divided by 30. 33 divided by 30. Okay. So here then it becomes 33 divided by 5 volt. Okay. So second example, write down this mesh equation for this circuit. Yeah. What we have here is 12K, 6K, 4K, 4K, 2K, and two independent voltage source, 12 volt and 9 volt. So how many branches are there? 1, 2, 3, 4, 5, 6, 7. The branches are 7. The node 1, 2, 3, and this one 4. So according to the formula which we have learned yesterday, the equations needed to solve this problem is b minus n minus 1. So 7 minus 4, 3, plus 1. 7 minus 4 is 3. I forgot now. 7 minus 4 minus 1, right? Then becomes 4. Is the equation. So first we draw, because there are also 4 meshes. We draw the mesh current here. First is the I1 to the leftmost mesh, then I2 at the middle upper part of the circuit, then I3, and finally I4 on the rightmost mesh. Then we write the mesh equation using Kirchhoff voltage law. At mesh 1, 12 kilo ohm, so according to passive sign convention, 12 kilo ohm I1, the coefficient for I1 will be just this one, yeah, and as well as here this one for 6K I1. Or otherwise we can do the traditional way. We go one by one through each of the component. So 12K multiplied to I1, then here plus 12 volt because there is a voltage drop here, then plus 6K multiplied to I1 minus I3. So in mesh 2 here, then if we depart from this node, then this is negative 12 volt because it is a voltage increase, which is a negative voltage drop. Negative 12 volt plus 4 kilo ohm here, I2 negative I4. Yeah. Then here plus 4 kilo ohm multiplied by I2 negative I3. At mesh 3, if we depart from this one, so this is voltage increase, so we have to assign negative. Yeah, negative 9 volt plus 6 kilo multiplied by I3 negative I1, yeah, plus 4 kilo I3 negative I3 minus I2 equals to 0. At mesh 4, if we depart from here, from this node, there's the voltage drop here, so plus 9 volt plus 4K I4 negative I2 plus 2K I4 equals to 0. So we have 4 equation with 4 unknown, yeah? I1, I2, I3, and I4. So which one here? 18K I1, negative 12 volt is this one here. This loop 1. Okay, I2. Okay. Yeah, here is from the, is it from this equation? I'm not sure. Equals to negative 12. So, oh, from the mesh one equation. From the mesh one equations, this is negative 6k I3, and the I1 part is 12k plus 6k. 18k I1 negative 6k I3 equals to negative 12 volt. Then the second equation becomes 8k I2, which come from here, 4k I2 plus 4k I2, 8k I2 negative 4k I3 from here, negative 4k I4 here, equals to 12 volt. So this minus 12 volt move to the right hand side of the equation. Okay. Then this one, the third part also similarly, I1 is the contribution to I1 is from here, negative 6k I1. I2 comes from this part only, so negative 4k I2. While I3, there are two coefficients related to I3 here, 6k and plus 4k. So here we write down plus 10k I3 equals to 94. And finally, the last mesh equation is negative 4k I2 plus 6k I4 equals to negative 9 volt. So you can choose the favorite technique to solve this system of equation. So you can use substitution, elimination, or immediately the easiest will be to put into matrix form and solve it using Octave or MATLAB. Okay, let's now uh, investigate special cases. Yeah? For example, this one, the first cases is where the circuits only contain independent source. So for example, here, the question is, we are asked to find both the V output here across the 6 kilo ohm resistor and V1. V1 is the node voltage just after the 2 milliampere current source. Yeah. Since we don't know the resistance, the internal resistance of the current source, normally ideal current source will have a 0 ohm internal resistance. So we don't really know what V1 is. So there is no relationship between V1 and the source current, however. So mesh 1 current is constrained. Yeah. Here, because the mesh current here, I1, basically coincide with this independent current source, 2 milliampere. So basically, we can immediately write down I1 equals to 2 milliampere. Okay. So the mesh 1 equation will be I1 equals to 2 milliampere. So current sources like this that are not shared with other meshes or loop serve to define a mesh loop current and reduce the number of required equations. So because so I1 already known, or I1 equals to the value of this 2 milliampere current source, because this 2 milliampere current source is not shared by other meshes or other loops. At mesh 2, then this will be 2 kilo ohm, I2 negative I1, then this is voltage increase, or basically a negative voltage drop, so negative 2 plus 6 kilo ohm multiplied to I2. So by inspection, we obtain negative 2 kilo I1 plus 8k I2 from here equals to 2 volt. Then we can calculate further that I2 so equals to 2k I1. So I1 is already known here, which is 2 milliampere. So the I2 will be equals to, this move to the right hand side equation, 2 kilo multiplied to I1, which is 2 milliampere, plus 2 volt, yeah, plus 2 volt here, 2 volt, then divided by 8k. So equals to 3 over 4 milliampere. So from here, since we already know I2, the resistance also known here, 6 kilo ohm, V out can be immediately calculated. V out equals to 6 times K 6K times I2, or 9/2 volt. So to obtain V1, afterwards, then we need to apply Kirchhoff voltage law to any closed path that includes V1. So in this case, it will be this first mesh, yeah, I1, or you could also use this one, the outer loop, yeah, to obtain V1, apply KVL to any closed path that includes V1. Okay, so this one can, yeah, we cannot apply in this case this mesh I1 because it has been constrained. Yeah, the current is constrained that I1 equals to this 2 milliampere. So then we need to apply it in the larger loop. So negative V1 plus 4K I1. Why negative V1? Because here current flows upward, right? It means from this is 0, so this is if it is a voltage increase, yeah, because then voltage increase, then and because this is a source, it means then when we write the KVL equation in terms of voltage drop, then we have to assign negative sign here. So negative V1 plus 4K I1, negative 2, because this is also another voltage increase, plus 6K I2 equals to 0. Another example, compute the V output, yeah, using mesh analysis. The mesh analysis of the VO, which is the voltage across the 6 kilo ohm resistor in series with a negative 3 volt voltage, independent voltage source. Yeah. So this is 3 volt, but the polarity is positive down, is at the bottom part, while negative is the upper part. So it means that the lower part is 3 volt higher than the negative part. So we can redraw it as this one, but then we have to assign negative value 3 minus 3 volt. Yeah. So here we have basically 3 meshes, yeah, within the circuit, 3 loops. If we are speaking about loop, you can also have the fourth loop is encircling the outer path of the circuit. Let's say now we consider mesh currents, yeah, mesh analysis. So it means we consider loop that does not unclose other loop. So however here, so we have 3 basically, yeah, I1 here, I2 and I3. However here, this first loop and the second loop each has already independent current source connected through it. So it means, and they are not shared. They are not shared by other loop current. So it means there are one way it becomes easy and straightforward. But on the other hand, yeah, there may be some catch later. Let's say we just follow and then write it down. Yeah, this mesh currents as defined by the current source. So I1 will be equals to 4 milliampere. It's the same direction, right? This loop I1 has the same direction as this 4 milliampere. I2 is opposite to the 2 milliampere, so then we have to assign negative sign. So I2 equals to negative 2 milliampere. At mesh 3, here, so from if we depart from this point, this node, 4 kilo multiplied by I3 negative I2 plus 4 kilo multiplied by I3 negative I2, negative I1, sorry. Then plus I3 multiplied by the 6 kilo, and then here voltage increase, so equals to voltage negative 3 voltage drop. So after that, we rearrange the terms, yeah, according to the loop current I1, I2, I3. The component of I1 will be from here, yeah, 2K, a negative 2 because there is a negative here. Component of I2 will be from here, negative 4K I2. The component of I3 comes from here, 4K plus 2K, 6K plus 6K equals to 12K I3. Then the constant here coming from the independent voltage source, we move it to the right hand side of the equation, so it becomes equals to 3. So from here, then we can calculate I3 from the system, because I1 and I2 is known, so we can just substitute it into this equation. Only I3 is unknown, and when we obtain here I3 equals to 1/4 or a quarter of milliampere, 250 microampere. Then the question is on VO, or the V output. So how to find the V output? We can, for example, apply also another Kirchhoff voltage law. So V output here will be equals to 6K. If we write down, let's say the loop equation of this KVL for VO, if we depart from here, so this become 3 volt plus or this is negative, yeah, negative I3 times 6 kilo ohm. Then yeah, this one, so this is plus V output equals to 0. So then V output equals to 6K I3 negative 3. So this is what you have here. Okay, and is it almost time? So so then from here we can calculate the V output. Another example here, find the V output here when it has this 4 milliampere independent current source and 5 volt in the other part. The V output here is the voltage across the 6 kilo ohm. So if we define two mesh, so we actually need the current flowing on this right mesh, and that's why we use mesh analysis. I1 flows through the current source, independent current source 4 milliampere. I2 flows through the independent voltage source 5 milliampere. So from here, it becomes a constraint. So I1 should be and must be equals to 4 milliampere. So here the loop current or the mesh current equals to the current in the branch because of the existence of this independent current source. So I1 equals to 4 milliampere. So from the mesh 2 here, if we depart from here, this is voltage drop 5 volt, then going through here, plus 4 kilo I2 negative I1, right, plus 6K multiplied by I2 equals to 0. So after rearranging, so we obtain here 4K I2 plus 6K I2 equals to 10K I2, right? And we insert this 4 milliampere to here. So this becomes 5 minus 5. If we put here 5 volt, then this 4K plus 4 milliampere equals to 11 milliampere. So we insert this 4 milliampere into this equation. Here becomes 4 multiplied by 4K for I2. Let's just write it down, otherwise then it becomes confusing. So this becomes negative 4K I1 plus 10K I2, okay, equals to negative 5. Okay. Then if we replace I1 with 4 milliampere, so this becomes negative 8. Negative 8, yeah, just negative 8. 4 I1 is 4 milliampere. Sorry, not negative 8. 16. minus 4K multiplied by 4 milliampere becomes negative 16 volt. Okay, negative 16 volt plus 10K I2 equals to negative 5 volt. Then 10K I2 equals to minus 5 plus 16, 11 volt, right? So I2 will be equals to 11 volt divided by 10K, something like that. So here becomes 1.1 milliampere, supposed to be 1. Yeah, this is okay. Yeah? So I2 here equals to 11 milliampere divided by 10. So equals to 1.1 milliampere. Okay. Then from there, the output can be calculated. If the output is here, I2 multiplied by 6 kilo ohm. I2 is already known, 1.1 multiplied to 6 kilo ohm. Okay. This is the same. So we actually need the current on the right mesh. Hence we use mesh analysis. This is the same. I1 equals to 4 milliampere. So at mesh 2, it will be negative 4 K I1, yeah, because it's the direction of I1 is opposite to the loop current I2. That's why here at mesh 2, we assign negative sign. Plus 2K, 12K I2, yeah, from 4 plus 6 plus 2. Yeah, 12K I2 equals to 0 because there are no voltage source. So from here, we would obtain I2 to be 4 over 3 milliampere, and then V output equals to 6K multiplied by I2 equals to 8 volt. Okay, so that will be all for today. We will continue next week with